Hi guys, my name is Rosati. I want to say thanks to the JuliaCon organizers for putting this together during the pandemic. I'm a physics PhD student here in Austin, Texas, and I'm going to talk to you guys today about Inflation.jl, the package I've developed for studying cosmic inflation. So to really do this talk justice, I need to tell you guys a bit about cosmology and inflation. So if you look, you might know that if you look far enough away in the universe, because light has a finite speed, eventually you'll come to a point where the universe is extremely young. And the younger and younger you go, the younger and younger forms the galaxies take. And eventually, if you go far enough, there are no galaxies. There's just a hot plasma from the Big Bang. We call this the cosmic microwave background. And it sort of looks like this. And you might have seen this map before. So this is a map of the whole sky, projected down. And the hot and cold spots here are measuring small fluctuations in temperature in the cosmic microwave backgrounds. But what you might not know is that these changes in temperature are incredibly tiny, about 1 part in 100,000. So if we look, say, at if you're a more observant person than me, you might think about this for a while and realize, wait a second, that means if the temperatures are very, very close everywhere, that means on this patch here and this patch over here, these are on opposite sides of the universe for us, but they have almost exactly the same temperature. And that's pretty weird, because a light ray could not have traveled from one end of our universe to the other in the time that it's been around, right? And we even know that, between the Big Bang and the time this CMB forms, light could only travel about 1 degree on the sky. So you think there's 360 degrees in a circle, right? Only traveling 1 degree. It's weird for all of the sky to be the same temperature when it hasn't had a chance to equalize. So this is usually called the horizon problem in cosmology. Nobody's exactly sure why the CMB is all the same temperature. That would imply that the Big Bang happened at all the same temperature. But there's no reason to expect that to be true. So there are a couple other commonly cited motivations for inflation too. Why is the universe flat, and where are the weird particles? For it to be exactly flat and not a little bit too much or too little matter. And we would expect to see some magnetic monopoles or other weird particles based on the theories of physics we have. But we know that they're very dilute if they exist at all. Okay, so cosmic inflation is kind of a way of solving these 3 problems. So the usual story of cosmic inflation goes that the universe, when the universe is about a proton in size, there's a period of accelerating expansion, and it fluffed up to a grapefruit in size, and then kept expanding afterwards without accelerating. What this period of accelerated expansion does for you is kind of shrinks the patch of the universe that we see today down to a really, really tiny patch of the pre-inflation universe. So the reason why we don't see any The reason why the CMB looks like it's all the same temperature is because it's all from the same tiny patch from before inflation. So that makes sense. That explains it. Okay, so how can we make this process happen, right? So you might know that in modern particle physics, we use quantum field theory, and particles are just excitations of quantum fields. And you might also know in Einstein's general relativity, most matter attracts, right? Like the sun and the earth are attracted, of course, but some types of matter can cause repulsion. It's gravity is not purely attractive in general relativity. So one option to cause inflation is to have some type of repulsive effect with gravity, or an expansion of space. It turns out one option for this is storing a lot of potential energy in a certain type of quantum field called a scalar field. And this is exactly the same kind of field that the Higgs boson that was discovered a few years ago is. Yeah, it's a scalar field as well. And kind of for free, this gives you, this idea gives you quantum fluctuations of the field. And these can give rise to the initial density perturbations that we can see in the CMB, those tiny temperature fluctuations. They can come from this process as well. Here's kind of a cartoon idea of inflation. Let's start with just Newtonian physics. So let's imagine, you have a literal ball on a hill. If you remember your Newtonian force laws, the force is equal to the mass times the acceleration on the ball, or equivalently, the force is equal to the derivative of the potential energy function with a minus sign. Okay, and then taking this force equation, we can solve for the solve for the acceleration. Set the equation equal to 0, and we get the acceleration plus potential derivative plus 1 over m times 1 over m. Sorry, is 0. Yeah, so you can do exactly the same thing for inflation. And the physics is a little more complicated, but it's exactly the same result. We have the acceleration plus the derivative of the potential plus one extra term equals 0. And this extra term just acts as a friction force. It shows up because the universe is expanding. So you think about inflation as just the field starts with a high potential energy. It gradually rolls down the hill with friction, and eventually picks up enough speed that it has no more potential energy anymore, and inflation ends. We know inflation ends when the field has too much kinetic energy compared to potential energy, and it dissipates this energy in a process called reheating. Basically, it spawns a whole lot of particles and dumps this energy into other fields. And so this is sort of how we think the standard model and particles, normal everyday matter and dark matter, and then whatever else in the universe got created is in this reheating process. Okay, so that might have been kind of a lot to take in, but let's recap a little bit. So we're just trying to study, a certain dynamical process for making the universe expand. How will we actually do that in practice? What can we say about it? What can we learn? So for the kinds of models my collaborators and I have been studying, there can be hundreds of interacting fields, not just one. It can be quite a few that participate in inflation. And in that scenario, we want to know, okay, what are the constraints we can put on it? What kind of potentials work? Do they predict the right quantum perturbations for our universe. And yeah, you can essentially reduce all the interesting questions into either solving ordinary differential equation or parameter estimation. So yeah, you're either constraining the parameters in a potential, or you're finding a new potential and solving. So that's why I started working on Inflation.jl. Well, it'd be more accurate to say I tried a few other things first. So the first thing I tried is I wrote the code in Mathematica, which, if you all know, it's kind of like a closed source, primarily symbolic manipulation tool. And that was okay, but I really wanted something open source and a little bit more performance. So I ported it to Python, added some new features. But my experience there was that the differential equation solvers are pretty lackluster. And SymPy, of course, is also pretty slow, even when you lambdify functions. So yeah, around that time, I heard about Julia and heard about the great differential equation suite, and I thought, okay, yeah, this is what I'll try next. And it's done really well. My code currently supports more fields than any other of the public inflation codes. So that's it's pretty nice. Julia's done well. So here's a rough flowchart of the code, or I also called it the grad student simulator, because this is what I do on a daily basis. So you start off by picking an inflation model, and you put it in the code. It'll do some symbolic calculations initially. This is one great strength of Julia, is because it has these metaprogramming abilities, we can get these as native code. So after caching those, we solve the background equation of motion, which is just the ball rolling on the hill. If we get enough inflation, we solve the perturbations equation of motion. We solve the perturbations equation of motion, which gives us the actual observables for the most part, the things we can measure in the cosmic microwave background. And if they're realistic, you're done. You can put it in a paper. If not, you can try doing some parameter estimation, either trying to prove this potential can't support realistic cosmologies, or that it can, and you find parameter values that allow for it. So we'll come back to this chart in a second. But I just want to mention that during this project, I had a lot of trouble finding the right symbolic backend to use to compute my equations of motion and my other tensor contractions and things I needed. I started with SymEngine.jl, but it really isn't complete enough to do what I needed. It doesn't have all the functions programmed into it. The next thing I tried was Reduce.jl, because it directly manipulates Julia abstract syntax trees. And this uses Reduce, which is a Lisp language symbolic backend, but it's kind of buggy because it's always communicating with this reduce binary in the background, and it's tied to x86, so I couldn't use it on my ARM laptop. The next thing I tried, which I'm still with for now, is SymPy.jl. And the only reason I've been able to keep using SymPy is because I found a workaround around lambdify. I've been able to find a way to convert Python SymPy expressions into Julia, native Julia quoted expressions that I can then eval and have a native Julia function out of. So I'll talk more about that in a second. I also tried just doing forward and reverse diff everywhere with no no symbolic steps, and that does work. You just lose a lot of performance when you're doing some of the tensor contractions numerically every time, instead of just doing them symbolically once. So I should also say I developed a package, symbolic.tensors.jl, which is also tied to Python SymPy. But the advantage with this package is that it can manipulate tensors at the abstract level. So you don't have to put in components at all. It's independent of dimension. So this is exactly what you want for highly dimensional problems. So I'm definitely looking forward to implementing that in Inflation.jl. I'm also gave a lightning talk about it, so I encourage you guys to watch that. I'll also say I tried modeling toolkit.jl a couple years ago, and it didn't really have the capabilities to do what I needed. That might have changed by now. I've heard it's improved a lot. Okay, so let's talk about how we put in the symbolic results and cache them. The setup is fairly simple. We just using inflation, using SymPy, linear algebra. This model, I'm typing in the potential here. It just depends on two fields. Set the field dimensionality here. So for now, it's just each field squared times a mass divided by 2. So it's kind of x squared times something plus y squared times something. You also have to define a metric on field space. Sets some types of interactions between the fields. For now, I set it to be the identity matrix. The list of parameters is here. For now, it's just the two masses and the parameter values. The initial conditions for the fields and their velocities. And then we just call this inflation setup function. This does all the necessary SymPy calculations, takes a bunch of derivatives of these and combines them, and stores that result in a serialized cache file, and gives us back a bunch of ready to go native Julia functions. Just to show you guys one of the functions, here is the equations of motion. So this is pretty much exactly what I showed you guys on the slide with the ball on the hill. The only difference is instead of time, I'm using a different variable to measure time. And here, there are two fields. And I'm also using SymPy's common subexpression elimination. So this x0 and x1 were determined automatically by SymPy to be a little bit more efficient to calculate it in this order. All right, so let's solve the background equation of motion now. And I'll just say I really love the differential equation suite in Julia. I'm sure I've said it a few times by now, but that's really what drew me in. This background evolve function is what I use to solve the background equations of motion. And internally, it's really just a call to differential equations.solve. There's a continuous callback that ends inflation once there's too much kinetic energy, not enough potential energy in the fields. Okay, and you might have missed it, but here we got 138 e-folds of expansion. So the universe expanded by a factor of e to the 138, which is plenty. Inflation only needs e to the 60 or so to match our universe. Okay, so we solve the background equations of motion. Let's take a look at the plot. So if you remember the potential, it's quadratic in both x and y. It's steeper in the y direction than the x direction. So we started off about equally in the x and y direction and fell down the steeper direction mostly at first and gradually turned down the shallower direction until we picked up too much kinetic energy and ended inflation. That's more or less what happens here. Let's check on our, so now we have this background trajectory done. Let's see if we can do perturbations around it and get our get something that looks like our CMB. Okay, so I have another, essentially just a wrapper around differential equations.solve. I also does the non-trivial step of converting the solutions of those equations into the actual things we can measure in the CMB. So in the CMB, we measure density perturbations following a power law. So K is a wave number, like a spatial frequency. So we generally expect there to be some amplitude and then a power law on the wave number. So this NS kind of measures the power of the power law. So if NS was 1, this would be a perfectly scale invariant power spectrum, what we call it. But we measured NS to be about 0.96. So it's not quite scale invariance. We've also looked for gravitational waves. So these would change the CMB in certain ways. And we know that they are at least at most 7% or so of the density perturbations. In our model, our amplitude was fairly close, about 10 to the minus 9. NS is not too far off. It's 944 here instead of 96. This is actually pretty tightly constrained, so this is actually projectable based on the NS. The R here is about 14%. I apologize for the big fluids. I had some rounding issues once and I never changed it back. But yeah, so we're definitely excluded here by the gravitational waves. So let's see if we can do better. Let's try some parameter estimation. One way we support doing parameter estimation with Inflation.jl, essentially just using black box optim, which is a great package, I think. So I'm just optimizing over this cost function, and the cost function measures the amount of expansion being at least 70 e-folds, and an estimate of NS, an approximate result, it's not perfect, measuring that to be close to 967, which is about the observed value. So you don't have to run it for very long. Even 5 seconds is enough to find some initial conditions that give us an NS that's much closer. Okay, so we can try evolving that solution, and we get something much, much closer. Not quite exactly on the approximate results, but not bad either. Yeah, we get an NS of about 0.960, but our R is still 14% or so. So this model is still excluded observationally. And through another argument, you can actually show that this model is will always produce too many gravitational waves. So they'll produce too much power there. So it's excludable entirely. But for the last few minutes of the talk, I just wanted to switch gears a little bit and talk about what I like about Julia and why I think it can do better and could take over more in my field than it has. I think Julia is very easy to write packages for. It's very easy to get large data sets into it. There's great access to machine learning and differential equations tools. The metaprogramming abilities are very nice for the symbolic aspects of what I do. But there's a couple of challenges as well that I think if we could solve them would really help spread Julia's adoption. If you don't know, in Python, there's a module called astropy, which is more or less a Swiss Army knife astronomy package. You know, it can keep track of astronomical units or help you plan observations, tell you where a star is at a given time from a given spot on Earth. Things like that, deal with common image file formats for astronomy, things like that. Also, IRAF is a pretty beloved piece of software by astronomers, and it's in desperate need of a port to a modern language. I have friends who haven't updated their OS in 7 or 8 years because they're afraid they'll break IRAF, and it's a huge pain to get it working again. So that was open sourced recently, and is just in need of a good port, and Julia could be the target. Yeah, so that's pretty much my talk, everybody. Thanks for listening. You can check out the Inflation.jl code if you'd like, my GitHub link. The scientific results me or my collaborators have found are at this Inspire link using the code. So special thanks to my collaborators. The names are there. In addition, I want to thank all the other groups that have been working on inflation simulation packages. I've definitely been inspired by most of them, or all of them. And I'm going to say thanks to them too. Yeah, so it should be in the chat if anybody has questions. Thank you.